few minutes late. In our today's agenda, we have several presentation of projects, with the first one of the presentation of our chair from Professor Dr. Matjaž Mikoš. So I will let him share his screen and continue to present our chair.
Yeah, but we agreed, sorry, Tamara, we agreed that Petra will introduce the catalyst talks in a few sentences. So Petra, please, before we start.
Yeah, I missed that because I was clicking everything
to
invite Simon and everything. So yeah, sorry, Petra. Then please.
As you prefer, please.
No, please, you can share your screen if you're able.
No, thank you. Just want to say that this initiative, this Resilience Catalyst Series Talks, is born under the umbrella of UNESCO and is part of the Resilience Program that is supported by the Central European Initiatives. So the purpose of this initiative, the Resilience Catalyst Series, is to begin to explore the role of the UNESCO chairs worldwide, focused on disaster risk reduction and resilience. And in doing this, we want to consider the complex interplay that is between education, science, and culture, which are the core key pillars of UNESCO, in transforming governance for building resilience to disasters. So, sorry, just introduce myself. I'm Petra Marizan, the program manager of the UNESCO Chair on Intersectoral Safety for Disaster Risk Reduction and Resilience at the University of Ljubljana. And with our chairholder, the Professor Stefano Grimac, who is here with me now, we warmly welcome to this third webinar in our Resilience Catalyst series. So far, we had the two very insightful sessions: the UNESCO Chair on Disaster Risk Reduction and Resilience Engineering at the University College London, led by Professor D'Ayala, highlighted the critical importance of multi-hazard risk and resilience in education infrastructure, and that she with their colleagues showcase some projects of the chair and collaboration they developed. And during this meeting, we also identified many opportunities for interaction with other chairs. This occurred also during the other talk that was led by Professor Tachikawa, the chairholder of the UNESCO Chair on Water, Energy and Disaster Management for Sustainable Development at the Kyoto University in Japan. And during the webinar, they provided an overview of their interdisciplinary activities on higher education for sustainable development in the fields of water, energy, disaster, and environmental issues. So, building on this momentum and also waiting for the other talks, we will follow yours. We are very honored today to welcome you, Professor Mikoš, and your esteemed colleagues from the UNESCO Chair on Water-Related Disaster Risk Reduction at the University of Ljubljana. And we sincerely thank you, Professor Mikoš, Professor, sorry for my mispronunciation, Russian, Dr. Klung, Professor Bezak, and Dr. Tamara Kuzmanic for organizing this session. Before we begin, a very quick reminder: the next talk will be on Friday 28th at 1 p.m., hosted by the UNESCO Chair in Informatics and Multi-Hazard Risk Reduction at Loughborough University. Professor Kiwa will share more details later. In the Resilience website that you will find in the chat in few moments, you can find all the previous records of the other talks, as well as this talk when it will be finished, and the registration for the next talks. So without further delay, Professor Mikoš and Tamara, the floor is yours. Thank you.
Thank you, Petra. I would like to say hello to everyone. Thanks for joining us, Professor Tachikawa, Professor Grimac, and all the other colleagues. Also my colleagues that have prepared, as you can see, further talks. So we would like to give you an overview of what UNESCO Chair on Water-Related Disaster Risk Reduction based at University of Ljubljana in Slovenia is doing. We have put a title, Enhancing Resilience of Water Structures, and then we have selected some causes, studies, and solutions from Slovenia. Hopefully, our presentation will be interesting, that you will gain insight into what we are doing, and also that we could decide maybe of some further collaboration within the resilience platform, and especially Resilient Catalyst. So without further ado, as you can see, we have, after my first introduction of the chair, 4 further 10 minutes or so talks about some more content about our work. So hopefully I will not be too dry with some facts and numbers. So our chair has this number 1134. We are based in Slovenia, and we have been established in 2016. So we have been afterwards prolonged in 2020 and 2024. So we are running now for the 3rd term. We are happy about that. And meanwhile, we got also a contributing UNESCO chair at University of Ljubljana, established just recently, few months ago, on sustainability education for teaching staff at another faculty at University of Ljubljana. So we have 2 chairs at University of Ljubljana in Slovenia, and in total there are 5 chairs in Slovenia. Slovenia is a small country, a bit more than 2 million inhabitants. We are proud that our UNESCO chair is a member of the UNESCO Water family. This is a very fancy name, but nevertheless, there are more than 170 intergovernmental hydrological program, or shortened IHP, national committees that are working in that field and focal points in these countries. We are running within IHP 16 IHP flagship initiatives. There are centers of the 2nd category, 29 are active and they are water related. And there are more than 80 water related UNESCO chairs, as well as unitary networks. So we are proud to be a member of that community. About our connections, we are, since our establishment, member of the UNITWIN, UNESCO, Kyoto University, International Consortium on Landslides, so-called Landslide Risk Mitigation for Society and Environment Cooperation Program. This is a UNITWIN. We are, as a UNESCO chair, member of that, and we are happy to collaborate with Kyoto University from Japan. Additionally, we are hosting our Slovenian National Committee for UNESCO Intergovernmental Hydrological Program. Of course, there are more than 10 members of that national committee. We are not very large, but we have a representative of the UNESCO chair is a member of the Slovenian National Committee. So we have some other leading roles in national Slovenian associations or committees. On one hand, Slovenian Academy of Engineering, then Slovenian Engineering Association, and Union of Associations of Slovenian Civil Engineers and Technicians, and lastly, Slovenian National Committee on Large Dams. Why is this so? Slovenia is, as I said, a very compound or small country with 2 million inhabitants, so mostly people in certain field of research are knowing each other. For us, it's much easier to do some social services and be involved in, let's say, most important associations in this field within the country. But our international network, I think, is also very important. It brings many advantages to us. We learn and we disseminate our knowledge, skills, and competencies to the international community. So we are members of various international bodies. We are member within advisory board of the flagship international sediment initiative within IHP UNESCO just recently. We are helping to promote UNESCO IHP 9th program. So we are working in several working groups within this 9th program. We are also working within IAHS, Help Indicate, within working groups, and we are also members of technical committees of the International Committee on Large Dams. We have some leading roles, not just being a member within international bodies. One hand, I called Young Professionals Network is led by us. Secondly, Global Promotion Committee of the International Program on Landslides and the Kyoto Landslide Commitment 2020, shortened GPC-IPLKLC, is led by us. Then we are also co-chairing a working group of UNESCO, a cross-sectoral theme on hydrological systems, rivers, climate risk, and water, food, energy nexus. And furthermore, we are also co-chairing IAHS helping working group on acceptance of nature-based solutions and their implementation guidelines. At home in Slovenia, also members of various Slovenian committees, let it be nominated or elected to them. Once there is a Council of the Republic of Slovenia for Higher Education, since we are based at University of Ljubljana, this is an important that we could, have an impact what is going on in higher education in Slovenia. Then there is a Research Council of the Republic of Slovenia, which is in charge for innovation, applied and based research. We have a member in this council. After floods, heavy floods in Slovenia in August 2023, government of the Republic of Slovenia established a certain council for reconstruction and resilience. So we are involved into increasing flood resilience in Slovenia. Two our members are member of the Council for Waters, which is at the ministry level, at the Ministry of Natural Resources and Spatial Planning, that is in charge, for legislation for a new water or water act that is 20 years old, and we would like to renew it. So these are some very good and important positions that we have. Furthermore, Slovenian Chamber of Engineers and Slovenian National Committee on Large Dams. We are based at Faculty of Civil and Geodetic Engineering. We are mainly engineers, civil engineers or environmental engineers. That's why we are so, bound to not just natural sciences, but especially to engineering sciences. We have a wide network of partners. In Slovenia, current partners are different UNESCO chairs, one on teacher education for sustainable development. Then at Institute of Josef Stefan, we are cooperating with chair on open technologies for open educational resources and open learning. This is much aligned with the UNESCO Open Science and Science-Based Education, very important collaboration. And in last 2 years, we also cooperating with the International Research Center on Artificial Intelligence. So how we could use AI tools within water management or for water governance. This is under the auspice of UNESCO, also based at the Institute of Josef Stefan. Then there is the first, I may say, the first UNESCO chair in Slovenia on cars education, based at University in Nova Gorica and at Research Center of the Slovenian Academy of Sciences and Arts. They are quite famous since they are, I think, for more than 30 years, they are leading and executing a PhD a doctorate school in karst research. And the last one, which I think is also important, we have connections to heritage site, UNESCO heritage site, namely Scotian Caves. They have a public service agency and we are cooperating with them. A lot of our work in last, let's say, years, but also currently, are international partners from especially UNESCO headquarters and Venice Regional Office, where we collaborate for the sediment initiative, flagship, and especially IHP NAST program. We are a member of the International Consortium on Landslide, ICL, based in Kyoto, Japan, since 2008. And each time we gained the so-called title of being a World Center of Excellence on landslide risk reduction. Then we have been working for International Research Society, Interprevent, based in Klagenfurt, in neighboring country, in Austria, since 1999, so for 25 years and more. We are a member of EuroAqua. This is a European network of freshwater research organizations. This is an important collaboration since we could, influence which type or which projects will be then sponsored in Brussels by the European Commission. If you're a member of such networks, you gain some insight, or you could know in advance what's going on to apply for research money of the European Commission. Then there are, of course, UNESCO chairs. Resilient Hands platform, we are really lucky and happy to help and work with chair on intersectoral safety for disaster risk reduction and resilience. Both colleagues are here, Petra and Stefano. Then in Florence, we have a member of ICL, another UNESCO chair, a very important and large one, on prevention and sustainable management of geohydrological hazards. Professor Nicola Casali is there in charge, chairholder. Then we have colleague today from the Wendy, chair on water, energy, and disaster management for sustainable development in Kyoto University. I was that lucky to be there at their inauguration a few years ago. Recently, we supported and are collaborating with another UNESCO chair on open water science and education. That's in Brussels, in Belgium, at Free University or Vrije Universiteit. And we are member of a Utopia Alliance integrated connected community, which is dedicated to digitization for hydroclimatic risk reduction. Utopia is an alliance of 10 plus European universities that was initiated by French President Macron. And I think there are more than 60 such alliances in Europe. And each university can be, member of only one alliance. So we are happy that we really proceed and work together with members within this alliance. And there is lastly IHE Delft from the Netherlands, where we are working more than 10 years quite successfully, collaborating to Erasmus Plus study program called Master in Flood Risk Management. Now, you could see from that yes, our title is water-related disaster risk reduction. So we focus mainly on floods, flash flood, river floods, pluvial and fluvial floods. On the other hand, on droughts, and also on rainfall-induced landslides. So if I have the last slide as just current projects we are working on in Slovenia, basically paid by our research agency, Research and Innovation Agency. And then we have some international projects. So we would like later on in these separate talks to introduce to you some of the current research projects that are running. So you can see that we are really working on a variety of topics. We are also working in the problems of reservoirs, sediment transport, dam engineering, let it be soil erosion, rainfall erosivity, for example, then on infrastructure, influence of climate change, then not to read all the titles, also, of course, flood and flood damages, fluvial erosion. From international point of view, we are working on several projects. There are given 5 that are running. There are 2, 3, or 4-year long research projects. The first one, nature demo, will be presented. Then there is the next one, Spawnscapes, the idea of Spawn City. And the third one is on the restoration of the Danube River Basin for ecosystem, called Danube for All. Then we have some more about torrential watershed management called Torrent. And the last one is UCPM, which goes into the civil protection mechanism in Europe called Boris 2, which is on cross-border risk assessment for increased prevention and preparedness. This is just a short overview. Hopefully colleagues will now go and present some more details on projects. I will stop sharing my screen, and the next one will take over.
The next one is Simon, Professor Dr. Simon Rusian.
Okay, thank you. I hope that you can hear me. Are you able to see the presentation?
Yes.
Okay, thank you. Is it okay?
Yes.
Okay. Thank you. Thank you for the opportunity to present some of the work that we have done in the last year. And so after the major flood event that we have in 2023, actually a lot of questions arise after that flood events. How well are we able to describe flood risk and flood damage during such an extensive event? So my presentation would be a short overview of the analysis that we have done in one specific study area, which was heavily damaged, of course. As for the presentation, I would just love to give you a short introduction related to the flood event. Then we will look a little bit into the methodology that we took to analyze the data and the flood risk and the flood damage. Then we will, I would just like to shortly represent the case study that we used. And finally, we will see and I would like to give you a short overview of the results and draw some conclusions. So probably you're all familiar with the situation, or at least partly familiar with this with the situation about the flood event in 2023 in Slovenia. Actually, approximately 1/3 of the Slovenia was quite heavily hit by this extensive flood event. It was caused by quite rare meteorological situation. Actually, we had a major flood event in the middle of the summer, which is, let's say, quite unexpected. The magnitude of the event was, as you can see from some of the numbers given here, quite extreme. And of course, due to this extreme event, extreme extent of the inundated areas, also there were a lot of uncertainties related to the estimation of the flood damage, and a lot of problem arise, as we will see, that actually caused a lot of, or introduced a lot of uncertainty in the estimation of the and evaluation of the flood hazard data that we already had. And of course, the estimation of the flood damage. Namely, during this flood event, what we have observed is that the flood hazard analysis that have been done in the past is, in some area, we found out quite a lot of discrepancies in the extension of the flood hazard analysis that has been done before the event and the actual situation during the flood event. And that led us to the idea that we need to introduce some changes in the flood hazard analysis, flood inundation analysis, and of course also in the flood risk and flood damage analysis in order to improve the possible extent of the inundated areas during the extreme events as was the event in 2023. So the main research aims during the study that we made was how to introduce some additional work that would help maybe the commonly used practices in terms of the flood hazard analysis by using the, for example, hydraulic model and hydrological model. So how to use the data from the event itself, which are available to derive, to get some data on the inundation extent and how to use this data to make, let's say, fast estimation of the flood damage. In order to do that, we use some special tools as FWDET and some global mapper tools, and we combine these tools with Krvavec software, which is a software that has been developed at our faculty and is actually a framework software that enables the flood damage analysis and includes basically a lot of information about the flood damage or the depth damage curves from different manuals from FEMA and also some specific flood damage data that has been gathered during past flood events in Slovenia. So maybe just a short overview of the methodological framework. We use the data that were available after the flood event, and we put this data into GIS tools, the before mentioned FWDET and global mapper, in order to estimate depths. And these flood depths were then inserted into the Krvavec software in order to get the flood damage estimates. So what were the data that were available? Fortunately, right after the flood event, quite detailed orthophotos of the areas that were hit by these flood events were collected. There were also some LiDAR data that enable us to analyze maybe some areas, some hotspots of the fluvial erosion processes and erosion processes in the headwater parts. Of course, we identified some lacks of the available field data in some areas, and also our environmental agency, which cooperates with us, also identified a lot of problems with the discharge gauging, as we can see from some photos on the right. Because during the flood event, the accompanying corrosion processes and huge amount of the debris caused a lot of problems related to the water level measurements at the water gauging station. And of course, this introduces a lot of potential additional problems in terms of the uncertainty related to the flood peak or discharge estimates. So based on this data, we try to delineate the flood extent by using firstly some automatic tools, but it proved that automatic detection of the flood extent is quite problematic. So most of the work had to be done basically manually by combining the detailed orthophotos and LiDAR data in order to derive the flood extent estimation. Further on, this flood extent estimation were introduced in the FWDET and global mapper data in order to derive the flood depth at the specific area, as we will see later on. This has been done for several catchments in Slovenia, but the main case study that I would like to present is the Meža River catchment, which is one of the most heavily hit catchments during this flood event, as you can see from also some of the photos. basically the situation in the major catchment could be maybe in best way described by looking at the headwater parts where we had really extreme amount of rainfall, very high discharges, which were accompanied by very intensive erosion processes and a huge amount of the debris. And locally, the estimates were made that the return period in these headwater parts could even exceed 500 years return periods. Further, we move downstream. We can say more evident was the prevalence of the fluvial erosion processes, accompanied, of course, by the huge discharges. But maybe one thing to notice is that further that we move downstream from the middle section, where the exceptional return period was estimated to be around 250 years. And then if we move further downstream in the lower section, of course, from these headwater parts to lower section, also the number of the density of the vulnerability elements also, of course, increases. But what we can see in terms of the flood event, of course, was the decrease or the less, let's say, less extreme return period of the flood events. From the maps that you can see here on these slides, these are the results of the flood delineation that was accompanied by the analysis of the water depths at the specific location. And these flood water depths were there inserted into the Krpan software. And Krpan software actually enabled us the flood damage quantification. So basically, the Krpan software includes the available state data about the number of people in the area, about the buildings, critical infrastructure, economic activities, industrial activities, cultural heritage, and so on. And actually, it enables the estimation of the flood damage for each basically category of the vulnerability elements that are considered in the Krpan software. And based on the flood extent and the flood water depth, we obtain some estimation of the total damage in this area, which goes up to approximately 77 million euros, which is quite high for this relatively small area. If we look at this flood damage quantification in terms of the return period, we can see that if we look at the official data on the flood hazard, which in Slovenia are made or analyzed for Q10, Q100, and Q500, we can see that these damage estimates are in the range of 3 to 350 year return period. Maybe an interesting additional information that is shown in the table below the graph is that we have an estimated annual damage of around 70 euros per capita during, for this flood situation that we encounter in this major river catchment. So by combining the available data on the after the flood event, by delineating the flood damage extent, and by analyzing the flood depths at a specific location, we were able to estimate the flood damage during this specific event, and in view, of course, also in the of other flood events with the return periods that are considered according to the Slovenian legislation. And the thing that that maybe we would like to point out that the return period of the flood event varied quite a lot at this specific location, but it was also quite noticeable elsewhere. In quite a lot of locations, we observed a lot of discrepancies in the flood hazard estimates that were done before compared to the actual flood event. This is, we believe, mainly the result of the huge intensity of the erosion processes and huge amount of the woody debris that caused a lot of local problems because it obstructed the hydraulic conductivity of the bridges and culverts and so on. So basically the flood waters were redirected in the areas that were previously not identified as being the one exposed to the flood hazard. And combination of the FWDET and Global Mapper and some other GIS tool actually enable us to make this a relatively fast flood risk and flood damage estimates. Of course, for this selected catchment, the major river catchment, but we believe that such an approach could be very helpful for the post-flood analysis in situation as we encounter in Slovenia, where we had a lot of problems with the uncertainties in the estimation of the flood damage. So this would be the short overview of the analysis that we have done in scope of the study of 2023 flood event in Slovenia, and I would like to thank you for your attention.
Okay, now our next presenter is Dr. Mateja Klun.
Good afternoon, everyone. So my presentation is loaded. I will just jump right into it. So my name is Mateja Klun. I'm also the member of the Chair on Water-Related Risk Reduction, stationed here at University of Ljubljana. My field of research are hydraulic structures and reservoirs. My main focus is structural safety and numerical modeling. Today, I will talk about ongoing projects at our chair in the field of structural health monitoring of dams. First, since I'm quite sure that majority of the listeners is not dams engineers, I will start with some basic definitions. First of all, we can all imagine that a dam is a structure built to retain water. But since I'm going to be talking about large dams, the definition of a large dam, it's an international definition recognized by the ICOL, International Commission on Large Dams, is a dam structure with at least 15 meters of structural height, and this structural height is measured from the lowest point in the foundation to the highest point of the crest. Also, dams lower than 15 meters can be defined as large dams if the reservoir is having more than 3 million cubic meters of water in it. We know different type of dams based on, for example, load-bearing capacity. We know there are gravity dams, arch dams, masonry dams based on the material they are built from. We know concrete dams, embankment dams. Basically, since every dam site is very unique, very specific, there is also probably as much dam types as there are dam sites, at least at some extent at some point. There are currently over 60,000 dams constructed in the world, according to the ICOL register. The unofficial number is probably even higher. And these dams were more or less actually built in the previous decades. The major part of dams are earth embankment dams. Almost 70% of them are like this, and majority of dams, globally speaking, are built for irrigation and drinking water purposes. Around 25% of dams in the world are built for hydropower purposes, for example. In the case of Slovenia, based on the definition of a large dam, we have 43 large dams in Slovenia, and the mean age of the dams is already 47 years. We have built majority of our dams before the year 2000, but also we had some active construction sites after the year 2000, and the last dam in Slovenia was built just 2 years ago, and the purpose was flood protection. The mean height of Slovenian dams is 28 meters. The highest dam, most of them, it's an arch gravity dam, which is 60 meters high. And majority of Slovenian dams and Slovenian reservoirs are basically multi-purpose reservoirs, and the most common combination is flood protection and hydropower. We also have 2 industrial dams. And a fun fact, 3 of our dams, they're called Klauže, are also enlisted as UNESCO World Heritage Sites. They were built in the 18th and in the 19th century as a part of a system for the Idria mercury mine, and nowadays they are basically a part of the technical history. These dams are still in function, they still retain water, and well, basically, if you have a chance to visit Slovenia, it's a good hike to visit those dams. Now regarding aging, I'm going to be talking about aging as well during my presentation. Dams, as any other infrastructure, anything else on this planet, are a subject of aging. So with time, properties of the dam structure, properties of the material will change, and we define these changes as aging. By definition, we talk of aging regarding dams after the first 5 years of operation. Here on this slide, you can see a graph of failure rates with respect to the dam age. And as you can see, there is a peak in failure rates in the first 5 years. These are failures that are not linked to any aging mechanisms. They are usually linked to something going wrong in the design or going wrong during the construction. And usually when something seriously is wrong, shortly after the first impoundment, also failures may occur. Even, well, failures occur either total failure or partial failures. However, if we look at the failure rate versus age in the later life cycles of the dam, we can see that the failure rate remains more or less constant. Saying this and also having in mind that when we are talking about dams and the design age of dams and the life expectancy of dams, the situation is a little bit different than, for example, in buildings when the design age is 50 years. Construction of a dam usually means a permanent change in the environment, meaning that the dams, here we can see 2 examples. One is the oldest dam in the world in Spain, is in operation for more than 1,000 years. The second one is Vala Dam from Slovenia, which is in operation for over 100 years. So basically, we are talking about very long life expectancies, and a lot can happen in this long life expectancy, including aging. Therefore, a very important aspect in maintaining the dams, in operation of the dams, is providing structural health monitoring. Basically, this is a very targeted approach by considering that every dam is a unique structure. It has its own properties, it has its own faults, it has its own operational procedure, history, site specifics, etc. And it has its own latent conditions. Basically, by latent conditions, I'm thinking often just by seeing a dam at a location, being there for decades, we could imagine, this dam is here for decades, nothing serious can happen with it, but in reality, it might have a hidden latent condition, which is just waiting for a proper triggering event to trigger it. So by having a structural health monitoring system for this dam, which includes, we first have to define all possible failure modes for this dam, based on dam properties, based on how we operate with the dam. And based on this identification of these failure modes, we also design the monitoring system for this dam. Basically, every system, every instrument, everything installed in the system is there to answer a specific question. So we prefer to have less instruments, but those there to answer a specific question than to have too much instruments and not knowing what exactly you're measuring. And basically then periodically evaluating what these instruments are reading and providing and performing a prognostic and diagnostic analysis. We are basically performing condition-based monitoring of this dam. And whenever, since we have a retargeted approach, we are measuring something with a sensor that might indicate that there is something happening with a potential failure mode, we intervene right away. In this matter, we are on a long term having a better chance of providing a solid structural safety of a dam structure. I will shortly present a study case from Slovenia. It's a study case of vibration monitoring happening on Brežice Dam in Slovenia. At this point, I have to emphasize that all dams in Slovenia are being monitoring. It's a legal obligation of a dam owner. Here in this study case, I'm just also presenting a case how vibration monitoring is included in the system of already existing monitoring. So we performed investigation on Brežice Dam, which is a dam built in 2017 on Sava River near town Brežice in Slovenia. It's a combined type of dam, combining of gravity dam, which continues into the two embankments, and the dam was built for the purposes of hydropower production and flood protection. The maximum height of this dam is 32 meters. It has 5 overspilling sections, and in the powerhouse, it has 3 units installed. The vibration monitoring that I'm going to be talking about is happening in the concrete part of the structure. So our investigation for this presentation is focused on the only concrete part of the dam. First of all, why even measure vibration? The reason is actually very simple. By measuring vibration and estimating the modal properties of the structure, we can very easily see what's happening with the material. Because the natural frequency of a structure depends on its geometry and its material properties. And if we are measuring also other factors on the structure and include also vibration monitoring, if we detect a change in the frequency spectrum, we are basically detecting changes in the material. If these changes are time related, we're actually measuring aging. Here we can see 2 examples of a jar. One is broken, the other one is unbroken. Basically, you can see the changes in the frequency spectrum, and here on the jar, you can also see the damage on the damaged jar. Similarly, with concrete structures, the main difference is that on a concrete, when we're talking about, for example, microcracking, we don't see damages on the surface. So when we're monitoring vibrations, we are actually looking at the damages that are not visible to the naked eye. So we are gaining an integrity information about the structure, which would be unavailable if we weren't measuring for vibrations. So investigation on Brežice Dam started already during the construction. So shortly after the concrete structure was built, we performed the first set of measurements. The reason was to obtain the reference date to measure the as-built characteristics of a newly built dam. This information now serves us for any further diagnostic and prognostic work we are doing on this dam. Later on, we had another big campaign of measurements on the dam. During the startup test of the hydromechanical equipment, we were also present at the dam structure and measured the structural response of the dam during basically almost all regular or emergency operational regimes that happened during the operation of the hydropower dam. Again, we use this information for perform diagnostics on what is the status of the dam, and also we use this information when we were constructing a numerical model of the dam. Using Diana software, we built a numerical model of the dam. In the model, we also introduced aging. Basically, we introduced aging by implicating a variable, a modulus of elasticity in the dam. And roughly speaking, if we introduced a 10% change in the modulus of elasticity, this reflected in about 5% of the change of the nectar of, or the first 3 natural frequencies of the dam. This investigation in total lasted for 4 years. So here I'm just briefly somehow capturing what was done. By the investigation, we were able to confirm that, first of all, vibration monitoring can be incorporated into the monitoring activities on dam structures. Besides the traditional methods, we also used portable vibrometer, and we were measuring vibrational response of the structure only during regular or irregular operational regimes. So ambient vibration tests were performed, and there was always enough excitation present on the structure, so we were able to perform the measurement. So there is no need to stop the regular operation to perform forced vibration tests. Only ambient vibration tests with the novel technology is enough. At the same time, we also experimentally proved that operational loads cause vibrations of the structure, and this is the vibration that is constantly present on the structure of the dam. Around 50% of the time, this low-level vibration is exciting the dam structure. And from the point of a concrete mixture, concrete matrix, basically this low-level vibration is a source that affects also the aging of the concrete. So it's something that should be considered on the long term. At the same time, we also confirmed that some of the excitation with the operation of the dam is close enough to the eigenfrequencies of the structure. So it's something that needs to be considered now and also needs to be considered in the future. Basically, this research sort of proved that when we are talking about structural health monitoring, when we are talking about structural health monitoring of concrete dams, including vibrations is a way to go. Now, I will just quickly mention there are 3 other projects in the field of dams and reservoirs ongoing at our chair. The first one has acronym Safety for TMF, which is targeting tailing dams and coordinated prevention and disaster management. It's an Interreg project, which is now 1 year into the 1 year ongoing, and we still have 1.5 years to go. And then we have 2 national projects. The first one is Modernized project, which is target-oriented project. And in this project, we are developing a methodology how to identify potential failure modes, which is to be used on dams in Slovenia. The third project is HRS, which is a project where we are researching the operation of run-of-the-river dams, with looking also at effective sediment transport during their operation with run-of-the-river dams. It was already mentioned, but members of the chair, we are also active in collaborating on international and national level. At this point, I would just like to mention International Commission on Large Dams, which is the leading association globally with more than 100 member countries in the field of dams, and Slovenia, with the Slovenia National Committee on Large Dams, is a member of this group. And I will just show for the last a beautiful picture of Tui Reservoir and conclude my presentation. Thank you.
Okay, next we have Associate Professor Dr. Nejc Bezak.
Hello, everyone. I will just try to share my screen. I hope you can see it. Is it okay? Yeah.
So hello everyone. My name is Nate Bezak and I'm also a member of our UNESCO Chair. And today I will show you one case study located in northern part of Slovenia, where university is only, and our UNESCO Chair is only partially involved, while the main work was done by the Tempos company, which is like engineering company working in the field of torrential and water management engineering. And this is like a kind of good example of case study for torrential hazard mitigation. So basically the case study, the study area is located near the ski resort. Like it's quite famous in Slovenia. It's called Krvavec ski resort. And as you can see in the map, so this is the location. I hope you can see it. Can you see my mouse? Yeah. Tamara? No?
No, not.
You
Yes,
have
yes,
a
yes.
presentation where we can see the next slide. Maybe you should
Okay.
switch the presentation mode.
Like this?
Right, thank you.
Okay. And now you can see the mouse, right?
Yep, I can see it.
Okay, so that's the location of the Krvavec area. And this is basically, these are two torrents called Brezovski and Lukanski Graben. And this is the location of the gondola lift that is taking the passengers to the skiers to the ski resort at the top of the hill. And as you can see, this is the location of the ski lift is like near, so a few meters downstream of the confluence of both torrents. So this is potentially problematic torrential area where we had low maintenance in the past. And since this is like quite important infrastructure, so the ski lift, it is important to keep it as safe as possible. And we had an extreme event, so local, let's say, almost summer thunderstorm, very short duration, that occurred during the May 2028. And after this event, we had an immediate response of the Slovenian Water Agency that invested quite a lot of money for the developing of all the plans and also for the implementation of the mitigation measures. And now we have, let's say, kind of ongoing research experiment in experimental catchment, where we are investigating different processes. And I will also show like the impact of the August 2023 floods on this area and how the mitigation measures that were implemented in this case study help to prevent the damage downstream. Okay, so in May 2018, we had an extreme event that lasted, a rainfall event that lasted for 13 minutes. So around 50 millimeters of rainfall was recorded in that period, which corresponds to around 50 years return period. And during the event and after the event, numerous landslides were triggered due to the heavy rainfall and turned into mass flows, so kind of debris flood. And as you can see in the photo, so the cabin ski lift was almost completely filled with sediments, so with the debris material, with woody debris, and caused quite a lot of damage on the ski lift. So the source of the material was in the upper part of the both torrents, so especially this Brezovski graben was quite active, so this was the main source of the material. Several shallow landslides were triggered. There was also a lot of intensive erosion in the channel network, while the deposition of the material, quite a lot of it was also observed in the Lukanski graben, just upstream of the confluence of both torrents. And as I said, so also a lot of it at the cable car station. So after the event, detailed geological survey was conducted, detecting the most critical parts of both torrents. and indicating the potential locations where we need to mitigate, to use some, let's say, engineering structures to mitigate the hazard mitigation in these two catchments. So basically, the mitigation, the conceptual design, was divided into three parts. So the first part was the mitigation of the Reka River, located downstream of the cabin ski lift. The second one was construction of the big check dam with silt in the middle, which is still ongoing. So this was the second phase, was not yet conducted. And the third phase was construction of multiple flexible net barriers in both torrents, so in the Brezovski and Lukanski Graben torrents. And the purpose, the most detailed focus of this presentation will be given to these flexible net barriers. So in total, there were 12 barriers planned to be constructed in the Brezovski Graben and 4 in the Lukanski Graben. So the main aim of these flexible net barriers was to reduce the channel slope and consequently to reduce the intensity of the erosion processes and therefore to prevent the mobilization of larger magnitudes of debris flows and floods. And so the engineering company, Tempos, that was designing these measures, closely collaborated with Geobrook company to define the most suitable position of these flexible net barriers and to define the most optimal dimensions, so the height and the width of these flexible net barriers. So basically, in total, as I said, there were 12 barriers in the Brezovski Graben. So the idea was to have not to afterwards to be able to remove the sediments, but to have like a stable conditions after the construction. So this is an example of the barrier, so flexible net barrier. So this the break rings, the abrasion protection, and some other details can be seen from this detail. So these are some photos that were taken during the construction, which was quite complex and problematic due to the difficult terrain and like the torrential characteristics of the area. So here is some videos. Here is one video showing the situation in this Brezovski Graben torrent after the construction of these flexible net barriers. So here in blue you can see the location of the cabin ski lift. And this is the photo after the construction. You can see the flexible net barriers. And this is the video showing the situation in the other torrents, of the Lukanski Graben torrent, also after the construction. So the video taken with drone, so you can see the flexible net barriers. So as you can imagine, so the main idea was to stabilize the slope and to also stabilize the banks of the torrents to prevent further erosion on the banks and also in the channel itself. Okay, and this is also the photo after the construction. Some additional photos of the flexible net barriers. So as you can imagine, the idea was that these barriers would be filled up with sediment slowly during the years. But then basically something extreme happened, and I will show you this later on. So as I said, so the phase 2, so the big slit dam with opening, with slit in the middle, is yet to be constructed at the confluence of both torrents, so at the confluence of Lukanski and Brezovski Graben. And as I also said, so this is also kind of experimental catchment for our UNESCO Chair, where we are observing characteristics of debris flows. So we have on the flexible net barriers, at some of them we have Geobrook GARD system installed, which is able to measure the impact and forces on the barriers, and we are also able to measure the corrosion of the nets. So we are doing periodical drone field surveys to detect the terrain characteristics in order to detect the amount of deposited and eroded material. And we also have this concrete abrasion monitoring, as you can see here on the right, where different plates of different types of concrete are installed to basically investigate the abrasion of concrete based on due to the sediment transport in this location. Okay, so then in August 2023, the extreme flood occurred that affected almost 1/3 of Slovenia. So around 10,000 new landslides were triggered. So there was huge damage, exceeding 15% of gross domestic product of Slovenia. So the return period of precipitation was over 500 years at some locations. And also here in this Krvavec area, we had quite extreme rainfall amounts. So as you can see here, we had over 160 millimeters in 12 hours, which corresponds to the return period of over 250 years. So numerous landslides and intense erosion processes are also observed in this area, and drone surveys show that close to 20,000 cubic meters of materials was trapped by the flexible net barriers, and additional 30,000 cubic meter was not eroded because these flexible net barriers were actually positioned in this torrential area. So you can see here, the left photo shows situation immediately after the August event. And if you compare it with the situation in May, so the right figure, you can see that basically there was no deposition of the material before the cabin ski lift. So this is mainly due to the construction of the flexible net barriers, as you can see here. So these flexible net barriers were almost completely filled with sediments, and really large amounts of sediments were trapped in this area. So this is some additional analysis that was done. So you can see the demo difference maps for both torrents. So the left one shows the situation for Brezovski Graben and the right one for Lukanski Graben. And the red color indicates the areas where we had the deposition of the material, and the green and yellow colors indicate the areas where we have some erosion areas. So you can see here, so with black lines, we have also the position of the flexible net barriers indicated. So, and this is the longitudinal profile of the Brezovski Graben. So you can see that a lot of material was deposited upstream from the flexible net barriers, while some erosion was also detected downstream. So here indicated with red, downstream from the flexible net barriers. But deposited material was, like in some locations, even 4 or 5 meters in height. So this yielded like these big amounts of volume that were detected. We also analyzed the relationship between the impact forces that were detected by the guard system in the torrents on some flexible net barriers and the rainfall, and you are able to found quite, let's say, relatively strong correlation between the impact detected on the flexible net barriers and the 30-minute rainfall amount, with a lag of 90 minutes. So basically 1.5 hours was basically needed that the material came from the erosion sources to the flexible net barriers. So at least the ones where the guard system was installed. And some important, let's say, take away messages we were able to detect them as a result of this analysis. For example, so the impact forces of over 100 G were observed during the extreme August 2003 event. So the specific peak discharges were over 5 cubic meters per second per square kilometer, and there were really big amounts of deposited and eroded material that were trapped by these flexible net barriers. So I think this is a good practice of solution that can be taken in such torrential areas to prevent damage downstream, and it's a good example of cooperation of the Slovenian Water Agency, university, private companies, and so on. And it's also a good opportunity to learn more about the characteristics and dynamics of the debris flows, debris floods, and so on. And yeah, we were also able to publish quite a few scientific papers about this topic, and currently we also have one additional one under review in Natural Hazard Journal. So yeah, that's it from my side. So if you have any question, we can talk about it later on.
Thank you, Nate. Now we have closing presentation by Tamara that you should not introduce yourself. I have taken the floor. So please, the floor is yours to introduce nature demo.
Thank you. Okay, no, I have the wrong. Okay. Okay, so I will only briefly introduce you to one of our ongoing projects on our chair. So it is a nature demo project with the full name Nature-Based Solutions for Demonstrating Climate Resilient Critical Infrastructure, or also Nature-Based Solutions for Climate Resilient Infrastructure. It's one of our younger projects. It started last year. And it is an Horizon project, and it aims to create, validate mainstream nature-based solution for protection of infrastructure against climate threats. So as I already said, the project started last year in May, and it will last for 48 months until the end of April 2028. The consortium we're working with is quite big. It's quite big. We have 23 partners from 14 European countries, and the partners come from different spheres and fields of expertise, from industry, academic organizations, research organizations, non-governmental organizations, and national authorities, and from the fields of civil engineering, environmental engineering, mechanical engineering, and so on. The consortium is led by a Czech partner, Digital Innovation Center. Work is distributed across 7 work packages, in which we will create methodology, which will be validated across extensive pilot demonstrations, demo sites, and good practices found in our demo sites will be replicated in our replicator sites. I think my computer is a bit slow. Okay, yeah. So the overall project aims in developing advanced methodology. It will create a digitally enabled methodology to catalog and evaluate nature-based solutions. It will validate the results with real-world evidence on those extensive demonstration sites together. Mam prezentaciju. to gather robust evidence on performance of those NBS across different contests. It'll provide replication guidance from the findings in demonstrators and formulate policy recommendations with the guidance for replicating interventions, engage local communities, address knowledge gaps, and overcome institutional barriers. How will we do that? With identification and parameterizations of nature-based solutions. We will categorize nature-based solutions for climate resilient infrastructure and evaluate them based on different aspects, including technical, environmental, economic, legal, and social. We'll develop a multi-scale decision support tool, which will serve as help for decision makers for selecting nature-based solutions for different infrastructures. And as I said, demonstrate effectiveness and mainstream for those solutions. As I already mentioned, a lot of work will be done in demo sites. We have 5 very different demo sites selected in Alpine space, biogeospheric area. Demo sites cover different hazards from erosion, landslides, droughts, and heat waves to floods, which will be covered by us. So our role in the project will mainly be demonstration site. We will cover Gradaščica river restoration works. Gradaščica river restoration works are divided into 3 phases, with phase 1A closest to the city of Ljubljana, 1D in the upper reach, and phase 2 with dry retention basin. So for our demo site, mostly phase 1A will be covered, and with the addition of phase 2, as in phase 1B, there is not that much of nature-based solutions incorporated into river restoration. Yes, the works on phase 1A have already started and are close to end. And phase 2 is only to be carried out, which will hopefully be carried out in the scope of the project. In restoration of river Gradaščica, there have been several nature-based solution elements incorporated into restoration, and only some of them include widening of the channel profile, additional some fish refugia, protective planting, including some riparian vegetation, live staking, and similar bioengineering techniques, and also restoration of river floor with some sills and similar solutions. So as most of the work has already been done in this reach, our main focus in this demo site will be monitoring and establishing of monitoring system with figuring what equipment, which parameters, timescales, and so on. And from the findings in our demo sites, it will serve as a guidance for replicators, which will potentially be some of the partners in Germany, Czech Republic, Slovakia, or even within Slovenia. Additional role at this project we have is permits and regulatory compliance, which will result in a deliverable document called public procurement strategy with some guidelines on getting all the papers done for implementing nature-based solutions for infrastructure. Currently, we're at month 10 of the project. I'm sorry I had to cover everything because as the webinar will be published online, I'm pretty sure that I'm not allowed to have all of the data before it's delivered and approved by Europe to have it published online. So yes, currently we are intensively working on a nature-based solution catalog. We cataloged near 100 nature-based solution types, which are grouped into different families of solutions. And for each of those types, we prepare a detailed description with characterization according to ecosystem services, technical data, and categorization, and more details. Maybe we can see it's something behind those drafts. But yeah, there'll be a detailed description for each of registered NBS types with associated hazards it could help with. This catalog will be published as one of our deliverables in a few months, in 4 months, I think, and it will be also published as an online interactive platform that is interactive catalog. Other thing that we are currently working on in the scope of the project is, as I mentioned, we are trying to set up monitoring at each of the demo sites, so also at our demo site, to select which parameters could be helpful for validating usefulness of nature-based solutions for each of the hazards, select equipment, and the whole monitoring system. And also we are defining infrastructure at each demo site that is at risk from each hazard. So, for example, we have water infrastructure itself, but also the main highway, which is one of the main connections through Mediterranean route. We have regional roads. We also have some hospitals and kindergartens, firefighters, and so on. And for those infrastructure, we are defining impact chains and hazards that are threatening it. So that would be all. If you are interested in the project, please follow our social media pages or our project website. So that would be all. Thank you.
Thank you, Tamara. So that was some presentations we have selected. We could add more, we could be shorter. We are now still well in time. We said that it should be less than 2 hours. So definitely there are still 12 people on the web that can make comments, ask questions. It is simply up to you. The floor is yours. Please just, even it is not necessary to raise hands, I think just switch on the microphone and the floor is yours, please. Are you so exhausted? Please.
I have a question. Hello?
Yes, you are.
I'm Aldo Primiero from Civil Protection Friuli Venezia Giulia. I have a question for Dr. Bejak about the barriers on the torrent. I was wondering if is foreseen a sort of maintenance emptying the barriers, or they will consolidate as they are now full of material, because I think maybe they are supposed to last more time before to be filled of material.
Yeah, thank you for this question. So So the main idea was also initially of these flexible net barriers was to basically to stabilize the situation in the torrents. So no removal of sediments was planned also during the design phase. So that's the reason that there is also this phase 2 of the construction of this big silt dam at the confluence of both torrents. So this, I can maybe show it again. Just a second. So this big dam with slits, so with the opening in the middle, is then basically here the volume, the design volume is around 15,000 cubic meters of the volume behind this big dam. And here the removal of sediments is also designed. So here the access road can be constructed to this location, while like there is no possibility to remove the sediments from the flexible net barriers, because like they are positioned like really high in the torrent and there is no access road. So the only possibility would be only to remove the sediments with helicopter, which is like could be very expensive. So this is the construction of this big dam is then like essential to basically to also to further in future basically to be able to retain the sediments not entering the downstream part of the river.
It's okay, Aldo? Or
Oh, yes, okay.
yeah, it is really such a terrain in both these torrents that you really cannot, move the material. What we could do is to add additional nets. This will lower the sediment impact, and a counterbalance is definitely this 14,000. So it will be lowered by a certain factor, the inflow of sediments, so it won't be such a large magnitude during extreme events. And due to the slit, this opening, partially the material will be not removed mechanically, but will be, flowing through the slit during next flood. So you should take both into account. But all of those are basically, because of this extreme event in August, they have filled during one, let's say, not so extremely event, because it wasn't several 100-year return period, but we were surprised that definitely all these were, filled during a few hours. But the idea is really to stabilize. The channel incision has stopped. It should be much higher, but it's not very easy to build like 8-9 meters high dams. There are 4 to 6, isn't it, Nate? Something like 4 to 6 meter high, not more.
Yeah. Mostly
it's not optimal, but there is no enough place to do a large dam, which would be, it's so steep that you are not gaining a lot of volume by raising the height. You have seen the longitudinal profile. There are a lot of places where you could put additional, you could put some more, and they will fill. But definitely the main idea is definitely this concrete dam, phase number 2, that should be built soon, hopefully.
I think it was a very high impact for the network, but if it resists that event, I think it will last for the next year, because maybe the material, if arrives in more years, it can more consolidate.
Yeah, but I think without these nets, it will be much worse than it was in May, I think May 2018, where there was less material, but it deposited much lower. Now it has been kept by net barriers. you would ask whether the next one will go across. So that's
yes.
why we need this large dam, definitely. Should be built. I think it has already been designed. It should just, money should be secured, and it's no problem to build it in 2 months or so.
Okay, thank you.
Yeah, Professor Mikos and colleagues, thank you very much for very important presentation. And I'm really sorry that very big flood disaster in 2023. This flood looks like very much similar that the flood disaster happening in Japan. And our experience is very much similar to the catchment in Slovenia. One was today's I learned from the presentation by Nate that net barrier works very successfully to reduce the disasters. And also in Japan, sometimes we experience recently is the dam reservoir works very well to store the debris wood. I think that Professor Simon mentioned about the debris wood, and really it caused a very severe disaster. And at first we did not realize, but dam reservoirs will store the debris wood. So I think that it will be recently, sometimes we experience such kinds of situations. And also in Japan, now our main target of the research is how to well utilize the dam reservoirs. Because to make the new dam reservoirs is not so much easy, and also to make the new retarding basin or infrastructure is not so much easy. So recently we are doing is how to well improve the function of the dam reservoirs. For example, very severe rainfall is expected, hopefully 2 or 3 days before the dam managers begin the release of the waters. So it means that to increase the flood capacity. And of course, it is not so much easy because the dam reservoirs, as you know, that hydropower generation or the water stored for the agricultural sector or daily life. So I think that for the waters or to store the water or to prevent the flood disaster, sometimes it causes different directions. So, but recently, the flood forecasting gradually getting better. So by using these forecasting, how to improve the dam reservoir operation is our main research and also actual operations. I think that today's presentation is very much similar to the Japanese situation. So we are very happy to collaborate with your chairs. Thank you very much for your great presentations. Thank you. Just not question, just I really feel that it's a very similar situation in Japan and Slovenia. Thank you.
Yeah, thank you, Professor Tachikawa. I was so lucky to see some of your during Interprevent or ICL forums or meetings situation, let it be in Kyushu or elsewhere.
Yeah.
So yes, you are investing much more money into from diverse ministries into disaster risk reduction. We are not that happy. We are comparably to Austria. You might know also the situation in Austria. We are investing much less money per capita, to say, or per kilometer of the torrent. So, for example, regarding dams and reservoirs, we are, just keeping 1%, maybe 2% of the whole water that is falling as rainfall. So we do not have a lot of reservoirs, and if we have them, they are more in lower reaches on larger rivers like Drava, which comes from Austria. So yes, with that, we can tackle more this, let's say, not lowland, but still larger rivers floods, where we are speaking several thousands of square kilometers. But since we are 60% covered by forest, and we are pretty hilly area, so basically we have a lot of torrential problems where you cannot have large reservoirs, there is no place, no volume. So what was for us kind of surprise last year, oh well, that was 23, already in August, a lot of landslides, close to 10,000, which would be one landslide per 2 square kilometers, were initiated, mainly shallow landslides, debris slides, smaller debris flows, and a lot of sediment flow into the rivers, as shown by Professor Rusian. So we have a lot of sediment inflow, what you are calling sediment-related disasters. That was a surprise for us, that was a lot of sediment coming into larger rivers and a lot of floating debris, woody debris. Since we are so forested and we haven't invested enough into forest management to, clear all the fallen trees out of the forest, and when such a large rainfall event is coming, then you are getting thousands of cubic meters of woody debris that makes problem at all of the bridges. And so it was a mix of that, and that's why if you have flood risk maps or flood hazard maps, and there are no scenarios on sediment and woody debris, just on clear water, that's not good. Then you are mistakenly thinking that other parts a bit further from rivers are safe, but this is not true. River morphology works, and we were proven by nature in August 2023 that we should really do our job a bit differently, using several scenarios for torrents and how to incorporate design floods, sediments, and woody debris into river engineering, so to speak.
Yeah, that's right. Not only the flood risk maps, I think that we need to think about the debris and sediment. Otherwise, it does work. Yeah, thank you very much. Thank you.
Thank you for your comment. Any other questions or remarks? Petra, you would like to ask introduction of the next one, or you have some remarks?
I don't know if
Petra,
please.
Petra, sorry, I have a question to the group of colleagues of Ljubljana about the scenario, Matthias. I completely agree with you about the use of scenario, that we have to take in account the real situation of the scenario, taking account not only the water problem, but also the breeze and also the I can say the geomorphological context where the problem happens. Because the question is how, if you have already done, you have think to link this scenario with the first responders, or in order to give a response in civil protection, starting from the study of scenario in advance. What means if you have some models that you can find that the scenario 1, 2, 3, 4 produce the failing of critical infrastructure, bridges, roads, or make the isolation of some little villages in the mountain, or floods. This could be a link with a different typology of response for the civil protection. Have you done something about this with your civil protection in Ljubljana or not?
I think Simon, Professor Rusian, might give some insight. There are two levels. One is definitely D1 for early warning system and for civil protection, disaster relief. At the moment, I think we are a bit more towards how to raise the flood resilience generally, how to move infrastructure, how to move new houses out of rivers, out of flood-prone areas. that should be defined not just by pure water, but taking woody debris, fluvial morphology like bank erosion and inflowing sediment into account. That's level of spatial planning. You have directly asked how to, go to the civil protection units and say them. There are, I don't know, 5, 6, 7 possible scenarios in this local case. Be aware, practice, observe, and react. This is, I think, the second stage when we improve this more general approach, but maybe I'm mistaken. Simon, what do you think, where we are at the moment?
Well, I only showed problems, right, during the 2023 flood event, but the fact is that when looking at the situation from the early warning system point of view and how the information was given or shared with the civil protection unit, generally, the general opinion is that this communication was rather good. Even if you look at these catastrophic videos from the flood events, a lot of people were actually, some fortunately, but some in more organized way, saved by the torrential water. So in terms of this early warning system, things, of course, there is still a lot of space for improvement. But and of course we have problem, how are we actually able to forecast such floods, because we have very, very little time. The last warning, I think if you look at the sequence of the warning that was issued by our environmental agency, actually the last warning, the red warning, came maybe 1 hour or half hour before the flood actually hit some areas. So this is of course one of the major problems that we are facing, but it seems that this information was quite effectively distributed to the civil protection units. Of course, the things that you mentioned related to the scenarios, there have been, I know that in some areas, there have been some scenario-based, let's say, flood hazard analysis conducted, but generally for Slovenia, we have our flood legislation, which considers 10-year, 100-year, and 500-year return period. If I'm not mistaken, in Italy, it's 30 years, 100 years, and 300 years. So maybe the way I see maybe to move things forward would be that the warning would give an approximate magnitude of the flood event, and since we have some flood hazard maps prepared, we could look at some areas where could we expect that the flood could happen. But again, we have a lot of accompanying sediment erosion processes, fluvial erosion processes, woody debris, which prove that can change considerably the path of the floodwaters in some specific areas.
Oh, yeah, we should say this was the largest natural disaster since independence of Slovenia, last 30 years plus. And nevertheless, with economic and not direct damage estimated with this post-disaster assessment, close to 10 billion, which is like roughly 15-20% of GDP, there were basically nearly no casualties, which is an indicator about the early warning system, how the people react, and our civil defense, I would say, is one of the best in the area. From old times, from the last Yugoslav times, we have taken that, and it is based on firefighters, basically. But we can improve it. We can improve it, definitely. I think we should go more to probability mapping, where you have these scenarios, where you play with different scenarios. But especially the state wants to make the whole region, the whole Slovenia as a republic, more flood resilient. and that goes into special planning. So we were, for the first time, able to ask people to move, to not rebuild on the same spot, to move, to go elsewhere and find, new houses elsewhere. So I don't know how many houses. I think the number was close to 500 should be removed. I don't know what will be the final number. I hope at least 200 or more will be replaced, built elsewhere. I think that's for the first time a sign that we should take mitigation rather now adaptation to move out. But we have a lot of houses that are still, built in last 30, 50 years in flood-prone areas, and it's not very easy to move and go away since you have land for food or you have unstable slopes. So it's a tricky game where to go to be safe and not to spoil, food production, for example. Agricultural land should be also protected. So we have some problems how to do it.
A lot of problems.
Oh, well.
Okay, thank you. But I think I agree that the future is based on the scenario approach. When you mention probabilistic approach and so, okay, but if you are able in advance to explore what can happen, you can prepare in advance or in the planning phase or in the early warning phase or in the response and recovery phase. I think that the goal is to take into account all the different factors, as you mentioned, not only the water, debris, the interruption of principal, roads and the forest effects and so on. You have to take into account the real scenario, if it's possible in advance.
I think since we are planning to have this special issue about new type of governance or how to change our attitude, there are already appearing AI tools that combine rainfall types, intensity, hydrological with hydraulic models, so that you could do this type of scenario playing much faster. I don't know whether they are good. I don't know, but they are, let's say in Germany, they use them. They can play in minutes to see what are the possibilities. And since AI, we know this machine learning, whether it is good or not, at least we can try that on existing examples, you might get some insight and make a reaction. And it is very important whether you can play in this 1 or 2 hours to really prepare on the situation that is coming, that will hit you, not to have some average general approximation. This is never, each flood is for itself. No flood ever will be the same as it used to be. So that's a problem. It's different.
Yes, thank you so much.
Thank you, Stefano. Petra,
Yes.
I think we should introduce the next speaker. It will be in 10 minutes, 2 hours, which is our limit.
Yes. I don't know if it's a representative from the UNESCO Chair in Informatics and Multi-Hazard Risk Reduction is in the chat or in the meeting. Let's see if
there are 12. I don't know.
I don't see.
Is with us.
Yes.
Aldo, Stefano, Professor Tachikawa.
Okay. No, so I will just introduce the next meeting that will be held on 28th February, Friday, from 12. Sorry, before I said from 1 p.m. instead it's from 12. The registration link is in the Resilience Catalyst webpage. So during this meeting, the UNESCO Chair in Informatics and Multi-Hazard Risk Reduction will present their activities with the high-tech informatics technology solutions for multi-hazard risk assessment and management. So we wait you all at participating in this presentation.
Great.
Thank you so much for your great presentations. And See you
if I
next
can,
talk.
Petra, last consideration for Matthias and also for the colleagues, because in our meetings and also UNESCO say pass from risk to action. I think your presentation today show the risk and the action and the solution, and also natural-based solution, but also solution for monitoring is a very good example to cover all the approach of the UNESCO and also the UN approach in disaster risk reduction and resilience. So my congratulations, and we will see next next meeting. Thank you so much.
Thank you, Stefano. Thanks for joining us, and I hope that some people will take opportunity to take a look at the video. You will put it on the webpage, as you said, Petra. So, and we will, I think, also put a link to your video to our UNESCO Chair webpage, where we are putting, publications and some of our work. So, it's any obligation to do that also for the UNESCO. I think we might also offer that this video goes to the UNESCO webpage where the invitation was announced. If possible, maybe you could take the lead to ask Lucille or somebody else how to put that.
Yes, we will.
Thank you very much.
Okay.
And
Bye-bye.
see you next Friday then. Is it?
Thank you.
Thank you. Have a nice day.
Bye-bye.
Bye.
Thank you.
Bye.
Bye-bye.
Take care.